So we looked at some of the surface winds and ocean circulation patterns, and another kind of movement of water in the ocean, which broadly I guess you could think of as a current, is coastal upwelling and other forms of upwelling as well. So what is coastal upwelling? Well, if you want to see what it is, just go to the Oregon coast almost any time in the summer and you will see it in action. So let's have a look at what this is all about. It's driven by winds, and in the case of the Oregon coast, it would be by the winds from the north to northwest, driven by winds that induce near surface water currents to have an offshore component due to Coriolis effect and Ekman transport. So that's a 4-minute video. I'm going to look at some of it with you here at least. Okay, so that gave us a little look at how the Coriolis effect plays out with the oceans. Ekman transport, pretty amazing that the net transport could be at about a 90-degree angle even from the surface wind. So what that means is if you're looking offshore in Oregon, I mean, you see if you go to the beach and you're looking straight out at the water, the wind's coming from your right, from the north, that you say, well, it's blowing almost parallel to the shore, so the current ought to go that way. And right along the shore it is. But once you get off at all in any depth of water, you'll start to see that bending off at an angle. And it's actually notable. When you're out in the water, like spend a lot of time kite surfing, and you can sense it when you're further offshore that it's a different direction than the wind itself. Makes for very different conditions because of that. So some things to think about. We just looked at this one on the video, and by the way, I would recommend you go back and watch the whole video. I just wanted to get you the basic idea here, because I know some of you probably haven't viewed it yet. And how can the Ekman transport cause downwelling? And that basically is where you reverse the movement of the wind the opposite direction so that the Coriolis deflection pushes the water onshore rather than offshore, and then that basically pushes a pile of water towards the shore and causes it to sink. That's what downwelling is. So this is significant on all west coasts, especially ones that are anywhere from tropical through middle latitude, say 50, 60 degrees north, and in all seasons except the low sun season. And generally in all latitudes except the Arctic and equatorial, and even in those zones in special conditions, you can get development of coastal upwelling. Cool, nutrient-rich water is brought up to surface, and in these settings, that facilitates a high plankton-based and algae-based productivity. So plankton are just these very small organisms, single cellular generally, that conduct photosynthesis. And then algae are also photosynthetic. They're just larger. And so the kind of classic alga that you might be familiar with would be like a kelp on the Oregon coast, if you know a little bit about the coast. And in either case, having cool, nutrient-rich water does facilitate high productivity. And those are the base of the food web. So beyond that, then the life above them that eats the algae or the plankton, and then the life that eats those things that eat that, and so on. You work all the way up to say, tuna and sharks, and so on. In the case of the Oregon coast, it does, and all places, it causes cooler surface temperatures as you do bring up that cooler water from below. The water at the surface during the higher sun season is almost always warmer than the water at depth. And it's often associated with fogs as well. And the shortest explanation for that is just because the cold water near the beach and near the shore is has an interesting effect. When the warmer water offshores that aren't upwelled, when wind resides or comes over those warmer waters, it picks up their humidity and then comes over the colder water. And because it cools off, it can no longer hold all that moisture like we learned about before. And so it condenses out some of that excess moisture picked up over the warmer water into that colder zone. So when you have fog on the Oregon coast in the late spring, summer, early fall, that's typically what it's caused from. It's observed also places where the wind blows offshore a bit, like in Central America, the trade winds blowing across the Central American Isthmus and Hawaii. There's some offshore component there blowing offshore, then creates pulling up water from underneath as well. Now, in the open ocean, we have. But one thing I wanted to say before we go there, one of the things that is amazing, about half of all of the tonnage of fish that are caught in the world are caught in upwelled zones. So when I say this is important for the biological productivity, it really is. This is a source of a large part of the human food supply, where those upwelled zones, whether they're coastal or in some other regions, are a huge part of the whole marine productivity. What that tells us is that much of the oceans are nutrient limited. The thing that upwelling does more than anything else is it brings up lots of nutrients, and you get a blossoming of life, flourishing of life, of productivity where that happens. So upwelling can also happen in the open ocean, and sea in mound-induced upwelling creates a nutrient-rich marine oasis and otherwise nutrient-impoverished ocean. So I'm going to have you view this independently, but that you want to go back to the PowerPoint and click on the seamount-induced upwelling. It's a delightful 4-minute clip from the Blue Planet series. And I have 1, 2, 3, 4 basic questions from that. Any one of those could be little exam questions. So just be familiar with those, kind of part of your notes that you know well and can locate for exam 2. I think you'll love this video. It's really, really amazing stuff. The other kind, which can be also in open ocean typically, is equatorial upwelling. And this is where you have converging trade winds near the equator. And how can that cause upwelling in this zone? So there's a diagram on the right side of the panel on this side. So when you click onto this in your regular notes, there's a description of that in there. And I think you'll find that narrative useful just to sort of understand equatorial upwelling. But literally, and around the equator, we do have upwelling, and it does employ the kind of Coriolis effect. Like I'll just jump there and we'll look at one little part of this just quickly. If you look at this, okay, so this is trade winds converging near an equatorial area. Okay, so these are the winds, and then Ekman transport. This must be see, this is southern hemisphere. The way they've drawn. No, excuse me, it's not. We're going this way, so it's to the right. So yeah, it's. I'm just looking at this. Is strange how they've drawn this. Um, the way it usually works is that the upwelling. I'm thinking of it. This is messing me up because I'm used to maps being north, and that's not really how it lays out in upwelled zones near the equator because equators go east west. That's what was messing me up. Anyway, here's a basic vertical profile. What you have is the winds are converging, but then there's a movement of water away from those arrows, and essentially away from the area where the wind would otherwise want to push the water to a pile there. Instead, what's happening is it's pulling the water offshore. That net transport of, say, roughly 90 degrees that we're talking about pulls the water offshore. And as it does, it kind of acts like a little light duty vacuum. It pulls up somewhat cooler subsurface water. And depending on where you are, there may be, maybe if it's really, really deep water, it won't be much improved in nutrients at all. But if you're in fairly shallow waters where that happens, then you can get some improvement in nutrients and see perhaps a higher biological productivity. By the way, that this site is it's just there's a whole bunch of stuff over here. You don't have to look at all this over here. Each of these are clickable, but it really is a great site because it describes the stuff we've been doing. If you just come to this particular page where you clicked into, I would recommend you read that. It reads like a really solid, fairly simple textbook, and you should really be comfortable with how upwelling works, whether it's coastal or in this case, equatorial upwelling on the right. So you got coastal upwelling over on this side. So highly recommended. All right, so going back to our notes then. Ocean currents and climate. With the El Nino Southern Oscillation, which is basically shifting pressures in the tropics. The El Nino is just a weakening or reversal of the normal east to west flow of the trade winds and surface ocean currents in the tropical Pacific. Sea surface temperatures rise in the eastern Pacific. Coastal upwelling and marine productivity are diminished during those years. The La Nina is just an opposite. It's like the kind of normal pattern of subtropical high pressure cells and trade winds on steroids, and makes for even more vigorous east to west flow. When you think about ocean currents in the broadest sense, enormous amounts of heat are transferred between the tropics and higher latitudes via the ocean currents, moderating climates in both regions. And perhaps the most important one of all is the Gulf Stream. So remember the thermal haline circulation diagram, and you bring all this very saline, very warm water up into the high latitudes, causing an enormously powerful zone of sinking, all right? Okay. Well, that changed the world history by making the very warm, the North Atlantic very, very warm. It also made the nearby areas that receive the westerly winds from the North Atlantic much warmer than they would be for their latitudes otherwise. So you have significant agricultural societies in Denmark, in the Scandinavian countries to its north, and the denser, higher populations in Northern Europe would not have been possible in a world of much colder temperatures there. So that Gulf Stream effect is just enormously important in world history, as so much of the kind of history of colonization and so on came from those large, dense societies that were very competitive with each other and so on in Europe. Now, you can opinionate whether you want whether that was a good thing for world history or not, but it's an undeniable part of it, and Gulf Stream was a very significant part of that story. And by the way, the Gulf Stream, as we think of it, didn't really exist up until about in geologic time, maybe 2.5 million years ago, because up to that point, the isthmus of Central America was a bunch of volcanic islands in an ocean, and there was a circulation between the Atlantic and the Pacific. So having that closed off by about 2.5 million years ago really changed how history worked. And this is just a quick look at some of the patterns, but you can see the cold currents coming in. Isn't that beautiful? The cold currents from the south, and of course the warm tropics. Hope you found the ocean currents section interesting.